In my last video about linear motors, I used an optical linear encoder because I already had it laying around. For the next version, I want to explore other affordable and compact encoder options, so in this video I will try to make one myself. Because of the extensive availability of cheap magnetic encoders, I took them as a starting point and wondered what really differentiates rotary and linear types. A translating magnetic scale essentially creates a rotating magnetic field, so the main difference lies in the field orientation relative to the sensor. This means that placing a rotary encoder upright above the scale should result in an output signal. As a first test, I moved the magnetic encoder scale sideways across a rotary magnetic encoder, which produced an output, prompting me to investigate further. Next, I designed a universal PCB to position the sensors in the middle of the scale instead of on the side, hoping to get a uniform magnetic field passing through the IC. I'm using a proper magnetic encoder scale in the hope of getting a more uniform and repeatable magnetic field in comparison to a stack of magnets. Be careful when buying cheap magnetic encoder scales, since mine had two defects in the pole pattern, which I noticed by going over them with a magnetic field viewing film. To evaluate performance, I built a test setup with two magnetic encoder scales and a linear rail to move the encoders across them. The upright rotary encoder is tested against the AS5311 linear encoder. The setup isn't perfect, but it gives a good general impression of performance. First, I tested the popular and inexpensive AS5600 encoder. The plot shows the difference between the reference and rotary encoder, resulting in a deviation plot. As you can see, it does work, but the accuracy is not good. Next, I tested the MT6701, which performed slightly better, but the performance is still not good. I tested both encoders with a pole pitch of 2 and 5 mm, and the 5 mm pitch performed better for both. I also tested a few different sensor distances from the scale and found 2 mm to perform the best. There are ways to improve performance, such as subtracting some harmonics, but since there are low budget options available that are specifically designed for this purpose, I don't think the extra effort is worth it. The CAD files and code will be available on GitHub, to which you can find the link in the video description, along with a list of parts I used. That's it for this video. If you have any questions, you can ask them in the comments below. Please consider subscribing, and I'll see you in the next video. Thanks for watching. Bye.